Well, good morning, good evening, and good afternoon. That's the wrong order, and hopefully you caught that. Welcome to the Crazy Hat Chemist. So here we go with another video here. Today's video is on gases worksheet number 1. So gases worksheet number 1. You're going to see that there are going to be, this is the first of 3 videos in this series, and this is for a general chemistry, introductory chemistry class at the high school level. So, and it can actually support your college chemistry class as well, or an honors chemistry class as well. All right, so first of all, what we need to do is go over a few of the equations and relationships that are written down up at the top of this worksheet, because that's going to be very critical. So the first one is P1 V1 T1 equals P2 V2 T2. This relationship is called the combined gas law or the general gas law, and it is it can also work with Boyle's, Charles, and Gay-Lussac's law. All right, so that's going to be very important. P is for pressure, V is for volume, and T is for temperature. Another item that we need here is that a temperature conversion, and that is right here highlighted in green. And that is going to be the degrees Celsius plus 273 is equal to the Kelvin temperature. All right, that's very important. So one thing that's really important in the whole unit of gases is to understand that every single time that we have a temperature with a gas law, we have to use Kelvin. It is absolutely a must, must, must. You must use Kelvin. So Kelvin is a must, and there is no degree symbol with the Kelvin temperature. The next relationship will be in orange here, and so let's highlight that. And that is called Graham's law. Graham's law is the rate of gas A over the rate of gas B is equal to the square root of an inverse relationship of either their molar masses or their densities. Well, 2 examples of all of these. The next one is going to be highlighted in yellow right here. Just take a look at that. And this is PV equals nRT. P is for pressure, V is for volume, N is the number of moles of gas, R is the gas constant, T is the temperature, must be in Kelvin. What goes along with this, and this is called the ideal gas law. So the ideal gas law. What goes along with this is the R, which is the gas constant, and that is written down right here. R is equal to 0.0821. The units to that is liters times atmospheres divided by moles times Kelvin. Okay, so that's very important. Then the next thing here is a lot of conversions of pressures. So this will be highlighted in pink right here, the conversions of pressures. So these conversions of pressures are as follows. 1 atmosphere is equal to 760 millimeters of mercury is equal to 760 torr is equal to 14.7 psi. There are many other units of pressure, but these are just the ones that we will be dealing with here on our 3 gas worksheets. All right, so without further ado, and let's keep on going. Let's do problem number 1. So number 1, it says the following: a gas in a vessel that occupies 350 mils. So what we first need to do is figure out this 350 mils. What is this? Excuse me. And this milliliters tells me what it is. It's this is milliliters represents a volume. So we're going to call this V for volume. Then it says at 2.5 atmospheres. We need to know what atmospheres is. Atmospheres is a pressure. So all these in the pink here are pressures. So everything that's in the pink is a pressure. So if you see these units of atmospheres, ATM, then that is a pressure. Now you see that it's 350 mils at 2.5 ATM. That means that these two things go together. And I'm going to call this volume 1 and pressure 1, since they are the first volumes and pressures that I'm seeing in this problem. Then it says, what is the volume? So that's really my question. What is the volume? I'm going to put a question mark right there associated with that of the gas if the pressure is changed to 1.1 atmospheres. So this is going to be volume number 2 because I don't, it's the second volume that I've come across. This is the first. And then this atmospheres is a pressure, and that is the second pressure that I've come across, pressure number 2. All right. So what I need to do is find out which relationship mathematically I'm going to use for this. I can use any one of these. I need to figure out which is the appropriate one to use because there's only one that will actually work. So if you see here highlighted in blue here, I have pressure 1, volume 1 over temperature 1 is equal to pressure 2, volume 2 over temperature 2. And this is actually the equation that we're going to use in this particular circumstance. Okay, so I'm going to rewrite this equation here. It's P1V1 over T1 is equal to P2V2 over T2, just like that. Okay. All right, so now what we're going to do is we're going to look and find out what we have here. So we have volume 1, so we actually have this right here. We have pressure 1, we have that right there. We are looking to solve for volume 2, and we have pressure 2. What we don't have is temperature. So that is making an assumption here, and that assumption is that the temperature is being held constant. This is actually called a Boyle's law problem. So Boyle's law. Boyle's law is when the temperature is being held constant and there is a change in either the volume or the pressure. So what we're going to do is we're going to plug directly into this Boyle's law problem equation, which is the general gas law with the temperature being held constant. Why is the temperature being held constant? There's no mention of temperature, so it has to be an assumption that the temperature is being held constant. That's where we're at. So we're going to plug into this equation here. Pressure 1 is 2.5 atm. The volume 1 is 350 milliliters. The pressure 2 is 1.1 atm. And the volume 2 is what we're solving for, volume 2. All right, so what we're going to do here is we're going to make sure that the units are the same. So whatever pressure is, these two units need to be the same of atmospheres, and they are. Then our volume that we solve for is going to be in milliliters since this volume is in milliliters. Okay, what we're going to do is simplify this and solve for V2. How we do that is we divide both sides by 1.1 atm. Divide both sides by 1.1 atm. Perfect, just like that. That will cancel this out here. And then what we will see is that the atmospheres cancels out and we're left with milliliters, which is a volume. Okay, we're going to be looking at significant figures throughout all these problems here because this is a multiplication division problem and this has two significant figures. This number here has two significant figures. That is, trailing zeros do not count unless there's a decimal in the number. So that 0 doesn't count, but it's important for placeholder. So it is still 350. This number has two significant figures. So what we're going to do is we're going to plug this into our calculator. We're going to plug in 2.5 times 350 divided by 1.1. And let's see what number we get out of this. So that's 2.5 times 350 divided by 1.1, and we're going to get 795.45. I'm going to round this to two significant figures, so that's 1, 2. I'm rounding with that 5. That is 5 or greater. I'm going to add 1 to the preceding digit. That 9 becomes a 10. I'm going to add 1 to the next preceding digit. That will become 800. Okay, now that number 800 only has one significant figure because these trailing zeros don't count. If I were to place a decimal there, then I would have three significant figures. So I'm going to have to do 8.0 times 10 to the 1, 2, 2. And that would have units of milliliters, just like that. So this is 8.0 times 10 to the 2 milliliters. And this has two significant figures. I'm going to circle that and say, done with that problem. That is fantastic. All right. Hopefully everybody's okay with that. That is our answer, circled correctly. All right, so now what we're going to do is we're going to move on to problem number 2. So I'm going to slide this up here a little bit so that we can see problem number 2. And it says a sample of gas is at the following conditions. 450 milliliters. So that is a volume because it says milliliters. And 640 torr, that is a pressure. If we have any doubt that that's a pressure, we should look up here and our pressure units have torr. So this is the first volume I'm coming across. This is the first pressure I'm coming across. It says, what is the pressure? So that is my question mark. I don't know what that is. That's going to be the second pressure. If the new volume is 560 milliliters, so this is the second volume that I'm coming across. All right, so what we're going to do is we're going to rewrite the appropriate equation here. And what is the appropriate equation? That is this equation, the combined or general gas law. That's right here. So I'm going to write that down. P1 V1 over T1 is equal to P2 V2 over T2. And again, what is not mentioned in this problem, temperature is not mentioned in this problem. And for those of you who really want to know, this is a Boyle's law problem again here. And this is Boyle's law. You can kind of look up Boyle's law and figure out what's happening with Boyle's law. Boyle's law is when the pressure volume changes with a constant temperature. Okay, this is an inverse relationship. If the pressure goes up, the volume goes down. If the pressure goes down, the volume goes up. That's kind of how this system works here. So what we're going to do is we're going to plug in our values. We have pressure 1, that is 640 torr. So that's 640 torr, just like that. And our volume 1 is 450 milliliters. That's 450 milliliters, just like that. Our pressure 2 is, I don't know, we're actually solving for that. Our volume 2 is 560 milliliters, 560 milliliters. Perfect. All right, everybody looking good. Now what we're going to do is we're going to solve this for pressure 2. So we're going to isolate this. So we're going to have to divide both sides by 560 milliliters. We're going to isolate this 560 milliliters. And you should see that when we do this, the 560 milliliters, that cancels out. I'm left remaining this pressure 2. I'm isolating that and solving for that. The milliliters cancels out, and you should see you have units of torr, which is a pressure, and that's a good thing. So we're going to type into our calculator 640 times 450 divided by 560, and that will be our pressure 2. So let's do that. 640 times 450 divided by 560, and that is going to be 514.28 in my calculator. Now, since this is a multiplication division problem, I am looking at significant figures. This has two significant figures, two significant figures, two significant figures, and this number will have two significant figures. I'm rounding with that 4, so that will be 510. The units that don't cancel out are torr. That is my pressure that I'm solving for. That has two significant figures. That's 510 torr. Beautiful. You guys are doing a fantastic job. All right, let's go for the next problem. But before we do, we're going to need a little word from our sponsor. Our sponsor for today's video is none other than the Crazy Hat Chemist. That's me. So please, you know what to do. I know you know what to do. Please watch the video in its entirety, number 1. Please subscribe to my YouTube channel. I would greatly appreciate that. Please give me a thumbs up. Please give me that like. I greatly appreciate that. And then please throw in some positive comments in the section there. I would greatly appreciate that as well. And of course, pass this on to all your friends who are in chemistry classes as well. All right, let's take a look at number 3 and find out what's going on with number 3. It says calculate the temperature. So that's the first temperature we're coming across. So I'm going to write that as T1. If the new conditions are 230 mils, that's a volume. 1.2 atmospheres, that's a pressure. And the original conditions are 400, on the original conditions are 450 mils, that's a volume. 22 degrees Celsius, that's a temperature. 2.5 atmospheres, that's a pressure. So this is temperature 1, volume 1, pressure 1, and this is volume 2, temperature 2, pressure 2. All right, perfect. Now, you should see that we're going to use the same generic equation. That's P1V1 over T1 is equal to P2V2 over T2. Now, this time, we are going to use everything in the combined gas law, combined or general gas law. That's what this is called, combined or general gas law. Now, one of the things that we need to do is we need to plug these in. So temperature 1, we're solving for that. So this is our unknown here that we're going to be solving for that. We're going to plug in our volume and our pressure for condition 1. Our first pressure here is 1.2 atm. And our first volume is 230 milliliters. Our temperature is unknown. I'm going to call that T1. That's what we're solving for. And then our original conditions are our pressure 2 here is 2.5 atmospheres, 2.5 atm atmospheres. Our pressure 2, our volume 2 is 440 milliliters. And our temperature is 22 degrees Celsius. All right. So one of the rules here is that all temperatures must be in Kelvin. So what we're going to do is we are going to look here at the top, and it is in green, highlighted in green. That's degrees Celsius plus 273 is equal to the Kelvin temperature. So I'm going to change this 22 degrees Celsius into Kelvin. So one of the rules here for gas law problems is that they all must be in Kelvin temperatures. Okay, then the reason for that is that there are no negative values in Kelvin, and all the gas constants use Kelvin. So we're going to plug in 222 plus 273. That's going to equal my Kelvin temperature. So 273 plus 22, that's going to equal to 295 Kelvin. Right there like that. So I've replaced this 22 with 295 by adding 273 to the 22. That gives me my Kelvin temperature. All right. Now, something to check here real quick. Are the pressure units in the same set of units? That is correct. They're both in atmospheres. Are the volumes in the same set of units? That's milliliters. That is correct. Is the temperature in Kelvin? Yes, that's correct. And I'm actually solving for temperature. It will be in Kelvin. So how do I solve this problem mathematically? It's cross multiply. So it will be 1.2 times 230 times 295 divided by 2.5 divided by 440. So I'm just going to sketch that out so that you can actually see that. So it's 1.2 atm times 230 milliliters times 295 Kelvin is equal to T1 times 2.5 atm times 440 milliliters. And we are still solving for T1. Let's see if we can roll this up here and you can see all of what I just wrote down. So we're going to divide now both sides by 2.5 atm, 440 milliliters, and we're going to do that to both sides so that we can cancel these out. So 2.5 ATM and the 440 milliliters, just like that. So you should see that the units of ATMs cancels out, milliliters cancels out. I'm left with Kelvin. So I'm going to put this into my calculator. It's 1.2 times 230 times 295 divided by 2.5 divided by 440. All right. So 1.2 times 230 times 295 divided by 2.5 and divided by 440. And that will be 74.018. We have to round this to the fewest number of significant figures. This has two significant figures. Two significant figures, trailing zeros don't count. Three significant figures, two significant figures, and two significant figures. So the fewest number of significant figures is 2. That's 1, 2. I'm rounding with that 0. That will be 74, and the units for temperature is Kelvin. And there we go. It's 74 Kelvin. It's not 74 degrees Kelvin. It's just 74 Kelvin. All right, fantastic. You guys are doing a fantastic job. We have 3 more problems to do. There's only a total of 6 problems on this worksheet, folks. That's not too bad. So we're going to slide this on up here, and we're going to look at this next question. This next question says, which gas is faster and by how much? So we got 2 questions within 1 question. Which one is faster and by how much in comparing hydrogen and carbon dioxide at the same temperature? This is a key critical component here, is at the same temperature. So we're going to slide this up and we're going to figure out which equation we're using. We're going to be using here for this problem number 4, Graham's law. This is Graham's law, which is the rate of one gas compared to the rate of another gas. It is an inverse relationship with the square root. So we're going to slide this up. We're going to go back to that problem. And we're going to write down the formula for hydrogen. Hydrogen is this formula of H2 because it's a diatomic. Carbon is carbon dioxide. That is CO2. Now what we need to do is we need to acquire their molar masses for both of these. So we need a periodic table. Let's go get that. All right, so here's our periodic table. We're going to use the molar mass for hydrogen. And on my periodic table is 1.01. I'm going to multiply that by 2 because the formula for hydrogen is H2. So the molar mass for hydrogen will be 2.02 grams per mole. Okay, now we need to get the molar mass for carbon dioxide. There is carbon, there's oxygen. Carbon dioxide is CO2 like that. So it's 12.01 times 1 because there's 1 carbon, 16.00 times 2 because there's 2 oxygens. Hopefully that works for you. So that will be a molar mass for carbon dioxide of 44.01 grams per mole. All right, fantastic. So now what we're going to do is we're going to answer the first question, which is which gas is faster? So we're going to take a look at the molar masses of these 2 gases. We've got hydrogen at 2.02 and carbon dioxide at 44.01. Which gas is faster? The fastest gas is the lower molar mass gas, and that is the hydrogen. So which gas is faster? Hydrogen. Hydrogen gas, which is H2. Okay, and again, just to clarify, how did I determine it's hydrogen versus carbon dioxide in terms of fast gas? The one that's a lower mass will move faster at the same temperature compared to the one that's higher molar mass. And so if you were to compare, let's say I'm going to be on a scooter and then you are going to be in a car, and you push me on the scooter and I push you in the car in neutral, which one goes faster? Me on the scooter with the same kinetic energy. So the faster gas is the lower molar mass gas. Now, how much faster is that gas is using Graham's law. So Graham's law states rate of faster gas over the rate of the slower gas is equal to an inverse of their molar masses. So carbon dioxide is down here. That means its molar mass 44.01 will be here, grams per mole. And then the rate of the hydrogen is, or the molar mass of hydrogen, 2.02 grams per mole will be there. It's an inverse relationship. And hopefully we're going to go back here up to Graham's law. You see that this is a B and that is B. And this is A and that is A. So it's an inverse relationship. That's why we made the inverse of it. Okay, so we're going to plug this into our calculator. So this is really 44.01 divided by 2.02. And then we're going to take the square root of that. And you're going to get the number 4.667668 over. Now, there is no other number in your calculator, but what is the denominator of this number? It's a 1. All right, looking good so far. We do need to round this here. And this has 4 significant figures. This has 3. So this has 4 significant figures. This has 3 significant figures. I'm going to round this to 3 significant figures. That's 1, 2, 3. I'm rounding with that 7. Add 1 to the preceding digit. 4.67 times faster compared to 1. So that means the rate of hydrogen is moving at a speed or 4.67 times faster than the rate of carbon dioxide, which is moving at a speed of 1 in comparison. All right. So if the number that you acquire with this calculation is greater than 1, as is the case here, then it's moving faster. If the number that you get is less than 1, then it's moving slower. That's simple. All right. All right, so let's move on to the next problem here, and that would be number 5. And we are going to take a quick little word from our sponsor, and that is, again, the second word in this video, and that is me. I'm the Crazy Hat Chemist. Please like, subscribe, all that kind of good stuff. Really appreciate it. All right, here we go. This one here is, what is the density of carbon tetrachloride? So carbon tetrachloride. First of all, we got to get the formula for carbon tetrachloride. That's carbon chloride tetra. So there's the formula for carbon tetrachloride. That's CCl4. Okay. The problem says, what is the density? So I didn't write the density problem up at the top, but I'm going to write the density problem right here. Okay. And that is density is equal to, well, you know me as the Crazy Hat Chemist, but my real actual true name, and you can probably find this out, especially if you're one of my students, is Phil Montbriand, and I work at Rio Americano High School in Sacramento, California, and my profession is that I am a teacher. This here is the density equation for a gas. So density is equal to PM over RT. P is for the pressure, M is for the molar mass, R is for the gas constant, and T is the temperature. And then we need to know what are STP conditions. That is standard temperature and pressure. Okay, so we're going to keep this really, really simple, stupid kind of thing. And the first thing that we're going to do is we're going to plug in the gas constant. And I'm going to scroll right up to the top here. What is the gas constant? It is R equals 0.0821 liters, atmospheres divided by moles Kelvin. So that's going to be critical in this here. So I'm going to plug that in for R, 0.0821 liters times atmospheres divided by moles Kelvin. In fact, this gas constant, that is R, okay, has this number and those units. There are 4 units associated with the gas constant, okay? The temperature under standard conditions is 273 Kelvin. That is super nice because, well, it's the conversion from degrees Celsius to Kelvin. So I've got now that handled, my temperature. You can see that my Kelvin cancels out. That's a beautiful thing. Then the P under that pressure is under standard pressure is 1 atmosphere. Now, if you were to look at my honors or AP chemistry videos, you'll find out that the standard pressure is not really actually 1 atmosphere, but most textbooks go for 1 atmosphere. It's really close to it. The real actual true number is 100 kilopascals. Now, M is for the molar mass. So we're going to look at our periodic table to get the molar mass of carbon tetrachloride. So here we go. We've already got carbon, that's 12.01. There's one of those. And there's chlorine, 35.45. There's tetra, that's four of those. So that's 12.01 times 1 plus 35.45 times 4. And that is going to equal 153.81 grams per mole. Now, what we're going to do is we're going to cancel out the units of atmospheres. We're also going to cancel out the units of moles. And what units are we left with in the numerator? Grams. What units are we left with in the denominator? Liters. So that is a mass per unit volume. That is most certainly a density. Now, what we need to do is plug these into our calculator. That's 1 times 153.81. So 153.81 divided by the gas constant, 0.0821, divided by 273, and that is the temperature, and we're going to look at, I think, three significant figures here. This, this number, this 1 atmosphere is a definition, so that's infinite. That's infinite. We'll call this an infinite definition here, and so we'll look at 5 significant figures with this number. We'll just stick with that. That will probably be easiest. So the number I get in my calculator is 6.834.3349. And I'm going to round that to 5 significant figures. 1, 2, 3, 4, and 5. I'm rounding with that 3. So I'm going to get 6.8343. The units are grams per liter. Grams per liter. And it's carbon tetrachloride. And that will be the number. And those are the units. And that is the formula. You guys are doing a fantastic job. We only have one more problem here left to do, and that is problem number 6. So here we go, problem number 6. If you have 0.0035 moles of oxygen gas, that's O2, at 1.4 atmospheres, that is a pressure, 37 degrees Celsius, that is a temperature. What is the volume in liters? So moles. So here is the thing. The question is, what do we have? What do we want? And how can we get there, right? And do you see do you see 2 of anything? Do you see 2 pressures, 2 temperatures, or 2 volumes? The answer is absolutely not. So consequently, we cannot use the combined gas law. What we're going to have to do is use the ideal gas law. So that's PV equals nRT. Okay, so this is the ideal gas law, and I am your ideal chemistry teacher. I don't really know if that's true, but I'm going to go with it for right now. All right, so here we go. Ideal gas law. And so what do we have? N is for moles. And so we do have that. We have the pressure. So we have the N for moles. We have the temperature. We have the pressure. We're looking to solve for the volume, and we always have the gas constant. So we're going to divide both sides by pressure, and then we're going to have V. So we're rearranging this equation. V is equal to nRT over P. All right, so this is the ideal gas law. We're going to plug into this here, and we're going to get our stuff. N is equal to the moles. That is 0.0035 moles. R is equal to the gas constant. We've used it once before in the previous problem, and it is right here. That is 0.0821 liters atmospheres divided by moles Kelvin. And then what do we have? We have the temperature, and the temperature must be in Kelvin. So I'm going to add 273 to this number. So it's 37 plus 273, and I'm going to get 310 Kelvin. Then the pressure is 1.4 atmospheres. You should see that the moles cancel out, the atmospheres cancel out, the kelvins cancels out, and I'm left with liters, which is a volume, and that's what we're solving for. So we're going to plug in 0.0035 into our calculator. We're going to multiply that by 0.0821. Then we're going to multiply that by 310. Then we're going to divide by 1.4. And we are going to get this number here. Volume is equal to 0. Let's scroll this up just a little bit more so you can see all of it. 0.063675. And how many significant figures? This has 2 significant figures. That has 3 significant figures because of that decimal. This has 2 significant figures. So I'm going to have 2 significant figures. Leading zeros don't count, but they're important for placeholders. So I'm looking at that 6, 0.064. And the units here are going to be liters. So liters of what gas do we have? We have oxygen, and that's O2. There we go. 0.064 liters of oxygen. Wow, that is fantastic. This is gases worksheet number 1. I think that you have been able to do this. I'm going to zoom on out here, and this is the entirety of this worksheet. And this is the gas worksheet number 1 here. We are going to have let's see if we can get all this on here. We barely got it, but we did. We can do it here, folks. This is 1 of 3 videos. Please like, subscribe, all that kind of good stuff. Throw out some comments. I greatly appreciate that. Hopefully you have a great day. And I will see you next time for more chemistry videos, especially on gases. Bye for now.